following is the details and objectives of this course. Please read it carefully and start the course. The ECU input-output factors in a common rail engine are similar to a gasoline engine. However, unlike a gasoline engine, a common rail engine is equipped with a boost pressure sensor for VGT control, a differential pressure sensor for DPF control, and an air control valve and a swirl control valve to increase power output and reduce emission. In addition, an airflow sensor and lambda sensor are also applied for EGR control. Lastly, an exhaust pressure control valve and a differential pressure sensor are added for Euro 5 LP EGR system control. Let's now learn more about each of these components. The airflow sensor installed with hot film is mostly used. The sensor's internal circuit is powered by 12-volt electricity, and it sends the change in airflow volume as a frequency signal to the ECU. The ECU uses the measured airflow data to control the fuel injection volume and EGR system via feedback. Two types of intake air temperature sensors are installed. One is embedded in the intake airflow sensor, and the other is installed on the intercooler. The sensors are NTC thermistors, for which the temperature and resistance are inversely proportional. The signal is used as a compensation signal according to intake air temperature, and also used as a compensation value and comparison signal for the coolant temperature sensor. The rail pressure sensor is installed on the common rail and measures the fuel pressure in the common rail. The piezo element inside the sensor sends voltage proportional to the fuel pressure to the ECU, and the ECU uses this signal to precisely control the injected fuel volume and injection timing. If the actual rail pressure value calculated by the pressure sensor is different from the target rail pressure value, the rail pressure control valve is used to control the rail pressure. The fuel temperature sensor is installed on the fuel feed line. It measures the temperature of the fuel that passes through the fuel filter from the fuel tank. The ECU uses the signal from this sensor to compensate for fuel volume. If the fuel temperature exceeds 80 degrees Celsius, it limits the injected fuel volume and controls engine output. The boost pressure sensor is installed in the intake manifold and measures the pressure within the manifold supplied via the turbocharger. The ECU takes precise measurement of air volume by using the pressure and air volume in the intake manifold and AITS signal to compensate for EGR operation and determine VGT operation. In case of excessively high pressure in the intake manifold due to turbocharger malfunction, the sensor detects this error and limits the engine output to protect the engine. The crankshaft position sensor reads the crankshaft rotation and detects the engine RPM and piston position. The camshaft position sensor detects the camshaft rotation and determines the TDC position. These two sensors play very important roles in determining injected fuel volume and injection timing. In case of sensor failure, the engine may not start, or if the failure is serious, the engine may stall while driving. The lambda sensor measures the oxygen concentration in the emission gases generated after combustion. This information is used by the ECU to control injected fuel volume and engage in precision control of the EGR. In addition, the fuel amount is properly controlled during maximum engine load in order to reduce emission created by rich fuel. The exhaust gas temperature sensor is used for detecting accurate exhaust gas temperature. It is applied to prevent the exhaust system or catalyst from being damaged due to significant temperature increase that can occur during DPF regeneration. This sensor is installed between the catalyst and filter. Note that post-injection is performed during DPF regeneration, and the exhaust gas temperature becomes higher than during normal driving in this process. There are two differential pressure sensors installed. One is for DPF control, and the other is for LP-EGR system control. The differential pressure sensor for controlling the DPF detects the pressure difference between the front and rear of the filter to measure the particulate matter collection, and it helps to determine the DPF recall timing. The differential pressure sensor for the LP-EGR system detects the difference between the exhaust pressure on the rear of the catalyst and the pressure in the intake manifold. This information is used for determining LP-EGR valve control. The glow plug heats up the combustion chamber via the heating wire in cold conditions. It improves fuel atomization and combustibility of fuel to reduce the exhaust fumes caused during an engine cold start. In recent models, the instant preheating unit is applied to allow glow plug control according to engine conditions. In this system, the glow plug can be PWM controlled through a relay unit by the ECU and FET element. As a result, the combustion chamber can be preheated even more quickly. The rated voltage for the instant heat glow plug is 5 volts or 7 volts. So take precaution when inspecting it, since it can be damaged if battery voltage is supplied. The air control valve is installed at the entrance of the intake manifold, just like the throttle valve in a gasoline engine. It closes the throttle valve in certain conditions to reduce the pressure inside the intake manifold. ACV control is mainly divided into 3 functions. First, the valve is closed at engine off to increase the engine pump resistance and reduce the vibration caused when the engine stops. Second, the valve controls the intake air volume during DPF regeneration to assist in increasing exhaust gas temperature. Lastly, it controls the amount of air during EGR precision control. The SCV changes the intake air flow by controlling a valve installed on the intake manifold. If the airflow is changed at a low speed range, the fuel mixes well with oxygen and it leads to increased engine output. This system can also increase EGR volume to reduce exhaust gas. Intake airflow is slow during low to mid-engine load, and this reduces air fill efficiency. In such a condition, the SCV is closed to increase the airflow speed. In high load conditions, the SCV is opened to supply greater intake air volume into the combustion chamber. The SCV can be diagnosed by using the actuator test in the GDS. In low RPM conditions, the variable vanes in the VGT are at an almost closed angle. The narrow passage of which the exhaust gas has to flow through accelerates the exhaust gas towards the turbine blades, making them spin faster. The angle of the vanes also directs the gas to hit the blades at the proper angle. In high RPM conditions, the variable turbine vanes in the VGT are fully open. The high exhaust gas flow at high engine speeds are fully directed onto the turbine blades. This allows high engine output and improved fuel efficiency in all engine load ranges. When you look at the VGT data in an actual vehicle, it shows that the VGT actuator duty is reduced during acceleration as the engine RPM is increased. This widens the narrowed exhaust channel and increases the exhaust fuel flow. At this point, you can see the boost pressure increase in the intake. Depending on the actuator drive method, either eVGT or solenoid VGT is used. Please review the lessons you've learned in this session through Simple Quiz. Let's wrap up what we've learned today.
Thank you.